Hello, everyone. Welcome back. Today, we're going to talk about linear regression, kind of what it is and why we use it. So, our goals for this are to understand, as it says, the basics concepts of linear regression. From, from that, we'll also want to be able to create a scatter plot of paired data, which is going to help us then create what's called a linear best fit line. Be able to interpret the slope of what's called a linear, this regression line or best fit line, then also be able to use this regression line to answer questions and help predict values. So first, let's just come over to the left and take a look at some definitions and some details. So first off, let's talk about what a mathematical model is. It says a mathematical model is an equation that's used to predict some kind of an outcome. It's usually based on physics or about data or both. So for example, when NASA sends a spacecraft into space to predict where it's going to go and how it's going to move, they use a mathematical model. It's based on physics, the physics of the situation. A lot of times we try to predict people's behavior. That's often used, you use that based on data we collect. And this is actually something that's very important. Lots of people, from governments to businesses, often will try to use data to make mathematical models to predict people's behavior that can help us then help them in their businesses or in their programs. Now, a common type of mathematical model based on data is called regression. Regression analysis, it says the process of finding an equation that best fits a set of data. This is also a process also called curve fitting. You may have heard of curve fitting before, more you've heard of regression. And so we try to fit data or fit a line, some kind of a line or graph data. That's called the best fit line. We want it to be the best one that fits the data. We'll explain a bit kind of what that means. Although how to do that is kind of beyond what we're going to do in this discussion. And linear regression means when we're going to use a straight line to fit data in 2 dimensions. You can also have linear regression in higher dimensions. Here we're going to focus on 2 dimensions. Now, with a line, and we've discussed lines before, straight lines before, the slope of a line is the rate of change. And basically, this is for a linear regression line or any line, the slope is the rate of change of the y coordinate with respect to the x coordinate. And for a straight line, this rate of change is always constant. And that rate of change often can help us to understand how a system, or how to interpret this best fit line and kind of what it means. And then we can determine from one data point to another how expected to change. Now, to create a regression line, we'll often start with what's called a scatter plot in 2 dimensions. A scatter plot is basically when we have data that we can think of in terms of x and y coordinates. And then we plot that data. These data become data points. And then for those data points, then we try to look for trends in the data, kind of see what the data indicates. And sometimes it would be hard to tell any trends at all. But in some cases, though, we can't actually see a definite trend. And then that's when we want to create this regression line or best fit line to kind of best fit that data. This also says if one data type can be considered the cause, we think of that as being your x variable or your independent variable. And if one variable is the effect, we think of that as being your y variable or your dependent variable. However, data doesn't have to possess a cause-effect relationship. This could just be a relationship between 2 different variables where one may not cause the other, but maybe help to predict the other. And maybe some kind of relationship between the 2. Then, as it says, a regression line is usually generated from the scatter plot data. Now, next 2 ideas, it says, as you see, they're called interpolation, extrapolation. We'll talk about those in a moment after we talk about our first scatter plot. So let's take a look at some data. And we're going to do this on Microsoft Excel. That's one of the programs you're probably most likely to use in the future, most likely to see in the future. So this is some data I found on the internet. This is my source, so you can look it up on your own. So for boys age in years from 2 to 12, this lists their average heights in inches. Now, so you'd enter data like this in a spreadsheet, and good practice, always put a title for your data, and then information. Now, if you want to make a scatter plot, what you do is you can, for example, highlight the first box, and you see this little box in the corner right here. Click on that. I'm going to drag this across and down either way until sorry, didn't mean to do that. Just a moment. I'm having some technical difficulties. Basically, I just want to, there we go. Let's start from that end, that will work. So what I did, I just kind of clicked. Okay, sorry. Yeah, I apologize for that. Don't click on that, but just click on the box, then drag it across, down, and across to highlight all the data you want. Then in Excel, where it says insert, and see where it says charts. So click on charts, little arrow, or pick on this first one where it says scatter. Okay, click on that and you already see a preview of it. So click on that. So that gives us our scatter chart. Okay, so once again, this plots for each one of those data points. This plots that set of data. So for example, for age 2, approximately 34 inches tall, right here, up to age 12, which is approximately 58 inches tall, about 59 inches tall. Now, a good practice to be in, let's go over the plus. Let's enter axis titles. That makes it easier to read and easier for if you're presenting as someone else. It's useful. So axis titles on this one first. So this axis title, backspace, and then put the title in. So this is going to be, I'll just do an AVG height. And then IN for inches. Come down, click on this axis title, do the same things. Let's go back. Sorry. There we go. I'm going to try that again. So go back, axis titles. I may have to start over. There we go. Let's click on that again. Axis title. So this is age. Or boy's age. And I'll just put it as YRS for years. Okay. Now, that's our scatter plot. Now, in this case, you can definitely see a trend here. This looks like it fits on a line pretty well. And it definitely is going up from left to right, or the boy's age increases, the height increases. And sorry, for some reason that stopped. You see I'm having a little technical difficulties here. So let's I apologize. I'm having some difficulties here. So average height, and once again, that's in inches. Okay, good. Now, so that kind of gives the idea of a trend, and it appears to be going up from left to right, which is what we expect. We expect as age increases, height increases. It's kind of a positive trend. So we expect have a positive slope to this. So now, that's a scatter plot. Now, often your trends, often they're not going to appear quite as well on a line. We'll see an example later where that's not the case. But that's what a scatter plot does, just allows you to see the data visually and kind of get an idea of what's going on better than just looking at a chart like this. Now, a regression line, let's explain how to do that in Excel. So click on the plus. See the very bottom where it says trend line, click on that and see that draws a line. Now, the line itself just is enough. So let's put this little arrow, because go down where it says more options. And this gives you choices. For example, here we're doing a linear, but you could use other kinds of best fit lines as well. And let's come down here where it says display the equation of the chart. Make sure we do that. Okay. So what this tells us then, what this shows us, is this is our best fit line for this data. Okay. And so what you're trying to do by best fit, you're trying to minimize the distance between the line and the vertical distance between the line and each one of the points. So this is the line that best does that. There are other lines you could draw through the data, but this one actually best minimizes the vertical distance between each point and the line itself. So this, we get a line, and so our slope is 2.4091, and our y-intercept is 30.509. Okay. Now, so that is a best fit regression line. Now, briefly, let's go back to our description a minute ago. In fact, let's talk about this line and talk about the other ideas of interpolation and extrapolation. So a moment, let's go back. So these two other concepts called interpolation and extrapolation. Interpolation says using a regression line to predict a value between data within your data range is called interpolation. But using data, so enter is kind of in between. Extrapolation is using a regression line to predict values outside your data range is called extrapolation, so extra or out. And now, a warning, you must be careful in extrapolating because sometimes the trends you see in the data may change outside your data range. And the regression line may not be good predictor. So let's go back to our graph briefly. So if I wanted to, if you notice our data goes once again every year from 2 to 12. What if I wanted to find, approximate the height for 5.5 years? What I would do in that case is for X, I would plug in 5.5 for X and get a value. That would be interpolation. Okay, so that would give me the value that's on this line right here. Okay, now that might not be the actual average, but based on this line, that would be the estimate you get. And also based on what we see from how well the data fit a straight line, that would be probably be a very good average. Now, extrapolation means going outside your data range. Let's say I want to predict the value for 13 years. I can predict that because remember, this is a line, it goes on forever in both directions. So I could also estimate the value for 13 years, plug in 13 for X, and then that would give me what that value is. Now, going a little bit beyond your data range is not necessarily a bad idea, okay? But think about this. We expect this trend is not going to increase. Once you get in your late teens, especially by early 20s, you stop growing in height. So expect in real life, this data would start to flatten off, but the line is going to keep going up forever. So if you plugged in a value for 50 years old, okay, that would give you something in the area of like 100 inches tall, or that would be over like 8 and 9 feet tall. That wouldn't make any sense. So that's a bad example of happening with extrapolation, is going far beyond your data range. You can plug in any X for this you want, but it's best to interpolate, use the values in between our data range from 2 to 12 years, or something really close outside that range. Because the way this data looks right now, this linear along a straight line relationship we see is not going to be true, most likely not going to be true everywhere within the age range of a male. Okay, so those are the basic ideas. Let's take a look at some examples. And work through them. Actually, just a moment, I need to make sure I have plenty of space for this. That should be enough, more than enough. So let's take a look at this example. Okay. In fact, I might even try and kind of move this over to the side so we can actually do some of the work beside it and below it. So let's see what this says. This says it's about ideal weight. It says Dr. J.D. Robinson also published the following estimate of the ideal weight of a man. Okay, this says 52 kilograms plus 1.9 kilograms for each inch over 5 feet. So what we want to do with that is it says we want to find a linear model for this estimate of ideal weight of a man using W for the ideal body weight and H, the height over 5 inches. Okay, so first, good practice kind of define what our variables are. So said our H is height over 5 inches. Okay, so H equals 0. That corresponds to over 5 feet, not 5 inches. I'm sorry, 5 feet. Okay. So h equals 0 is 5 feet. H equals 1 is going to be 5 feet, 1 inch, and so forth. Okay. And then our W is the weight in kilograms. Okay. Now let's see what makes sense. So we want to create a line, draw a line for this. We create a linear regression line. Basically, it's going to be a line that fits this data. Okay. That's going to look like W is equal to MH plus B. Okay. Where H is your height, W is your weight, and also M, these come from, so M is your slope, and B is the y-intercept. Okay, so this is from the equation of a line. Now, we're given these things here. So we're starting out. Let's read this first part again. It says this, Dr. Robinson published the following estimate of the ideal body weight for a man. So 50 kilograms plus 1.9 kilograms for each inch over 5 feet. So at 5 feet, what we want then is the weight is going to be 52 kilograms. So remember, this is 1.9 for every inch over 5 feet. Okay. And this once again corresponds to h equals 0. Okay. At 5 feet. All right. Now then our slope. So then what this tells us, then our B, our y-intercept is going to be 52. That's our y-intercept. Okay. Where since your x coordinate, or h is like our x here, is 0, that's 52. Okay. Now our slope, M, it gives us that as well. The slope, it says basically it's changing 1.9 kilograms, increasing 1.9 kilograms for every inch over 5 feet. So the slope is equal to 1.9 kilograms per inch. Okay, hopefully that makes sense. So for every inch you increase, increasing by 1.9 kilograms, that's positive because you're increasing. Okay, if it was decreasing, it would be negative. So our regression line, our mathematical model, is W, our weight, is equal to 1.9 H plus 52. Okay, and that's our mathematical model. Okay, that's what we're going to use to estimate things. Okay, so once again, we wanted a like a best fit line. In this case, it's not really a best fit line, just a regression line, since we don't have any other data specifically. We're just basing this off this initial value and then the slope. Okay, our amount is increasing per inch. Okay, and so that's part A. That's our linear model. Now, let's look at part B. Part B says interpret the slope of the model. Okay, B, the slope, M, which I'll just repeat, it's just 1.9 kilograms per inch. So we expect, what that means, what interprets it, is we expect the weight in kilograms to increase by 1.9 kilograms for every inch in height. Every additional inch in height. Okay, so that's what we expect to happen. Part C, a man is 5 feet 8 inches tall. What does this model predict his weight to be? Okay. Part C, for 5 feet 8 inches. Let's write like this. So what is the weight? As a question mark. Okay, well, 5 feet 8 inches, what that means, remember 5 feet was 0 inches, so 5 feet 8 inches means that h is equal to 8. Okay, so plug this into our model. And if we plug that in, what we get, let's go back to our model here. So W is equal to 1.9 times 8 plus 52. Okay, and if we plug that into a calculator, so 1.9 times 8 is 15.2 plus 52. Make sure you check this on your own. Should be 67.2 kilograms. So what this model predicts is that for someone who is 5 feet 8 inches, their ideal weight should be about 67.2 kilograms. And once again, that's probably not going to be exact or even this of the average. That's just what the model predicts. That may be a good estimate. Okay. And part D asks, if a man weighs 70 pounds, what model does predict his height should be? Okay. So if weight is 70 kilograms, let's put it this way, height with a question mark. Okay. Now, once again, look at our model again. Okay, this time, instead of knowing h, we know w. So w this time is equal to 70. So we plug this in. And so w is equal to 70 is equal to 1.9 h plus 52. And now this time we want to find what h is. We want to solve for h. So first, subtract 52 from both sides. And so that's going to be 18. That's 1.9 h. Then divide 18 by 1.9. And depending on where you round that off, let's just round it off to, I'm going to round it down. I'll make this approximate. Those little squiggly lines are approximate. H is going to be, erase that and make those look better. It's going to be approximately about 9. Remember, this is 9 inches. Okay. So the height of this person is, I was going to say approximately, I'll also abbreviate that. Approximately, remember, so h, remember this starts from 5 feet, so 5 feet 8, or sorry, 9 inches. 9 inches, 5 feet 9 inches. So okay, so that's being able then to use the model. So what we've seen so far in this example is we created a mathematical model. Okay, we understood what the slope tells us, and then we also use the mathematical model to find weight. We know the height, and then to find the height, we know the weight. Okay, let's look at our next example. Okay, and let me adjust this so we can move it around. Okay, let's read this one. In fact, this probably just going down the next page, make it easier to work with. Start on a new page. Let's see what this one says. This is about a parachute. So this one says, Rate of descent for parachutes says the U.S. Army is considering a new parachute, the Advanced Tactical Parachute System, a jump at 2,880 feet using this parachute system lasts 180 seconds. So part A is like before, so I want to find a linear model. So like we did before, let's kind of define what everything is. Now here says relating altitude A in feet and time in seconds. So T equals time in seconds. Let's make that S, and then A is the altitude or the height in feet. Okay, so we want then something once again linear, looks like this. A is equal to M T plus B. Okay, where this once again, this is the slope, this is the y-intercept. So now this time what's different is we're not actually given the slope right away. So you have to think about this in terms of points. So in the past, you've seen how to find the slope, because if you know 2 points on a line, so this is going to be a linear model, be a straight line. If you go 2 points on a line, you can find the slope. Okay. So we need 2 points on a line. Let's see if we can get that from what we're given. Okay. Now, what it tells us then is it says a jump from 2,880 feet, system lasts 180 seconds. Let's think about converting that then into data points. Okay. So the jump starts at 2,880 feet. What time is that? Well, that's our height, right? That's our altitude. What time is that? That's time 0. Okay. So that point is going to be at time 0, t equals 0. Our height is 2,880. Now let's think about this. Now the next point says it lasts 180 seconds, where time is our independent variable. So at 180 seconds, where are we? What's our altitude? Well, it should be, let's assume it's going to be 0. Okay. So there are our 2 points. Okay. So at time 0, you're at 2,880 feet. At time 180 seconds, you're at the ground, you're at 0 feet. So now our slope, our formula for the slope is y2 minus y1 over x2 minus x1. And here, it doesn't matter which you call y1 or y2, but just be consistent. So if I start with this y, I have to start with this x. Let's do that. If I start with this y, or actually let's do this way. Let's start with this y. And so that's going to be 2,880 minus this y, which is 0. And since I started with this y, I have to start with this x. This is going to be 0, then minus 180. Okay. And so this can be negative 2,880 over 180. Now, let's divide that to a value that's more useful. And it may or may not come out evenly. We'll see. It does. Good. So that value then, m is equal to negative 16. Let's think about the units of this. So y, remember our y are units. This is altitude. This is in feet. Our x units are in seconds. That's feet per second. What that's telling you, the negative tells you it's going in a downward direction, or you're decreasing, which you expect. Okay, we're starting from this height. So it says basically we expect then to lose from this parachute jump about 16 feet for every second we move through the air. Okay, for every second in the fall. Expect to lose an average of 16 feet. Now, once again, in reality, that may not be exact. They may not be constant all the time, but for our linear model, that will be. Okay, so that's what our slope means. Now, what about our y-intercept, our b? Well, actually, we know that. This is our y-intercept. Okay, when x is 0, that's our y-intercept. So b is 2,880. Okay, so our linear model or linear regression line, our equation we're going to use to predict the height for a given time is a, our altitude, is equal to negative 16 times t, our time, plus 2,880. Okay, so that's a model, then a linear model, straight line model we use to predict for a given time after the jump, then what your height is. Now, also this idea of talking about interpolation and extrapolation, obviously time could go past 180 seconds, but it won't make any sense. Then you start getting negative values. Okay. Now that was part A. Part B, yeah, find the rate of descent. Actually, that was what we found with the slope. So B, the rate of descent, is our slope m, which is equal to negative 16 feet per second. And once again, remember the slope for a straight line gives you the rate. And so this is the rate of descent. We expect to lose about 16 feet approximately for every second we're using the parachute until we get to the ground. Okay, then part C, find the speed of the parachute at landing. Okay. So let's think about how we can do that. So what is the speed? Is that related to something we know? Actually, it is. Okay. So the speed, oops, that's an S, not a C. Remember, speed is distance divided by time. In this case, that also equals the slope. Okay, is equal to, in this case, the absolute value of the slope, the absolute value of negative 16 feet per second. Because here, for speed, we just think about absolute value. The negative gives us the direction, so that's going to be 16 feet per second. And once again, that should be, based on this, should be constant. Okay, based on this model. So our speed then is our rate for a linear function. Okay, all right, let's look at our next example. So once again, give me a moment to get it. Okay. Let's take a look at this example. So here's our description, and here are questions that go with it. So let's read this. So it says, energy consumption. It says table 6 below, lists US fossil fuel consumption as percentage of total energy consumption for selected years. Now, this time, the linear regression model has already been determined for you, so we won't have to use Excel or anything to do that. Okay, for X represents the years since 1985. So kind of like the one we did for number 1. So 1985, X is 0. And Y represents the corresponding percentage of fossil fuel consumption. Okay, now, here we have this data. Okay, now this one, first part says do a scatter plot. Okay, now actually I'm not going to do that because that's exactly what we showed a minute ago in Microsoft Excel. So what you do is just put in your years in one column, and then your consumption values percent in another column, and then first do the same thing we did before, then to do a scatter plot. Okay, on second thought, we probably should do that anyway. So let me start another sheet, and let me kind of minimize this. I think I can move this over here. There we go. Okay, so let's actually just do that anyway. So here, this is going to be year. And this is going to be consumption. And once again, that's in percent. And just put in our data. So 1985, 1990, I just like to put the X's in first. So 1995, 2000, 2005, 2010, and 2015. Now let's put in our Y values. So first year we have 86, for 95 we have 85. Sorry, if that was not for 1990, 1995 we also have 85. 2000 we have 84. 2005 we have 85. 2010 it's 83%, and 2015 is 81%. Okay. Now once again, to create a scatter plot, we hit insert. Well, first we do that. So just click on like this value, then just drag this down and to get you all of your values. Hit the chart and then hit your scatter plot. Okay. Now here's a good example of something that you can see. It's not as linear as the first example looked at. So the data looks like a straight line should fit it pretty well, but it's definitely not as nearly on a straight line as it was before. So let's actually do, I won't spend all the time with the trend line, just put a trend line in. So that would be our best fit line. As you can see, in this case, there are definitely some differences between the data values, some of the data values, and the line itself. But this is a line that would actually be best at minimizing all these differences between the points, the Y values, the points, this vertical distance between the points and the line. Okay, so that's your scatter plot. So for this, then, I'll just say for the scatter plot, we'll do that on Excel. And then, of course, you can also find your trend line, which should be the same as this trend line. Okay. Now, B, interpret the slope of the model. Okay. The slope, here we definitely see this trend in data. It's decreasing, right? It's going down from left to right. So apparently the percent of fossil fuel usage is decreasing, although not an incredible amount. Okay, each time we go from 86 to 81, but it is decreasing. So the slope is negative. That is M first. The slope is equal to M, which is equal to negative 0.14, and that's percent per year. Okay, what that means is that the percentage of energy consumption by fossil fuels per year. Okay, as we see, it's decreasing. So it's decreasing by kind of that's based on what's in the slope of this line. That's how much it's decreasing per year. Okay, based on the slope of the line. Now, once again, you can see this likely true in every case. Okay, some cases it goes up here, for example, it goes back up before it comes down. But based on this line, that's the slope of that line. That tells you kind of approximately how much it's decreasing per year. And that's B. Now, use the model to predict fossil fuel consumption in 2025. Okay, so our Y, part C, okay. So I'll just say, so find the value in 2025. Now here, let's mention that our X, like the first example we did, X represents the years since 1985. Okay, so in this case, for 2025, X is going to be 1985. Basically, 1985 is our year 0. Then this is going to be 40 years after that. So 2025 is going to be X equals 40. Okay, let's plug that in. And so what we get then is y is equal to negative 0.14 times 40 plus, and what was our y-intercept? 86.18. Okay, now use a calculator to do that. Let's find what that value is. So negative um, and that value should be about 80.58%. In 2025. Now, if you notice, that goes beyond our data. That was actually extrapolation. So we have to be careful about extrapolations because this trend, which may fit a straight line reasonably well right now, may not fit a straight line into 2025. So we have to be careful about that kind of data. That's what it predicts, but it may not be very accurate because it's going outside of our data range. So remember, if we go inside our data range, if I want to pick the value, say in 2012, that would be interpolation. But going beyond either, like say 1980 or to 2025 as just did is actually extrapolation. You have to be careful about that because these data trends we see in this set of data may not be valid outside that range. And then finally, part D for this example is use the model to estimate the first year for which the fossil fuel consumption is less than 80% of total energy consumption. Okay. Well, the best thing, let's see, probably the best thing to do there, we could set up either as an equality or an equation. So let's just find as an equation, then we can understand it from that point. Okay. So for here, that's going to be our y. Okay. For y equals 80, then we want to find x. Okay. And so for our model, our y is 80, we want to find x. So plug that in. So if we do that, then that's going to be 80 is equal to negative 0.14x plus 86.18. And now we want to solve for x. So subtract 80. So that's going to be, we subtract 86.18 both sides. That's going to be negative 86.18. Negative 0.14. And also be careful with your signs. Our x should be positive, and it will be because we're dividing a negative by a negative. Let's divide this. Divide 6.18 by both being negative 0.14. And what I get then for x, let's turn this around, x, in fact, let's do approximately again. Obviously, round the nearest whole number. X is approximately 44, okay? Now, remember that's not year 44, okay? So the year is 1985, or was it 1985. Plus 44, and that should be 2029. So based on this model, okay, so that year is, so first year, now that's actually the first year should be equal, so first year below, so the first year, I'm trying to squeeze everything into this page, first year less than 80% is then going to be basically 2030, okay, based on this model, which once again, as extrapolation, it may not be that accurate, but that's what this model predicts. All right, let's look at one final example. Okay, and this is a good example. This kind of shows you what kind of, so a lot of times what real data can look like, especially if we have a lot more data. So we'll read this one. This says, this figure contains a scatter plot of 100 data points for black walnut trees and the linear regression model for this data. So basically want to interpret the model. Okay, now what this is the height. That makes sense. That's in feet, the height of the tree. This DBH is something that made it make a lot of sense. What the DBH is it says it's called diameter at breast height. Basically, it means is try to be kind of a system way of measuring the diameter of trees. So you measure it basically about chest level, about 4.5 feet in the air. Okay, compare the diameter of the tree, and then what we're trying to do then is compare the diameter of the tree to the height of the tree. Now, this is not expected to really be a cause and effect relationship, but just see if there is some relationship. It does appear to be. Now, look at the scatter plot of all these data points. See, it definitely appears to be an upward trend. So as we would probably expect to begin with, as the diameter of the tree increases, then the height goes up, and that makes sense. As trees get older, they increase the diameter, and they also get taller. Once again, this is not a cause and effect relationship, though. We could even make this one our X, this one our Y, but also get a similar relationship, basically the same relationship. And this is also our best fit regression line here. So you see this is the line that best fits that data, the straight line. You see it doesn't fit all the data very well. Okay, but that's probably, there's no really other discernible trends we can see in the model except probably something linear. Now, so that's basically interpretation. I want to start to interpret the slope of the model. So part A, the slope, which is 1.66, so M, which is 1.66. In fact, sorry, I need a little more space to write this. Let's go down here. So M, which is equal to 1.66. And this is basically the height in feet divided by this diameter breast height in inches. Okay, so basically the interpretation, what it means is for every increase of 1 inch in DBH, this diameter at breast height, we expect (1.66 feet) increase in height. Okay, so that's what the slope means. So for every 1 inch increase in this diameter, we expect 1.6 inch feet, remember that's in feet, increase in height. Okay, and once again, as you can see by the graph, that's not going to be true for all our data points. But once again, that's what the slope of the line is. That's what it tells you. That's our mathematical model for this. Okay. Part B is basically what we just said. It says, what is the effect of 1 inch increase in diameter breast height? That's going to be an increase. What we expect is an increase of 1.66 feet in height. Okay, and then part C and D are similar to what we've done before. So I want to estimate. So let's estimate the height of a black walnut with a DBH of 12 inches around the nearest foot. Okay, so here this is our DBH. So our DBH is our X is our DBH. As we're treating as an independent variable, okay? And once again, that's going to be in inches, okay? And so that's going to be, what I'm going to do then is for X equals 12, find Y, which is our height. Okay, so plug those in. And so from our model up here, let's look back at it. It's a little hard to see. Y equals 1.66x minus 5.14. So Y equals 1.66 times X, which is 12, minus 5.14. Double check that I said that right. Okay, then plug this in your calculator, and we'll find out the height. And what I get says this is going to be equal to 14.78 feet, and then rounded. And so this is approximately the nearest foot. This is around the nearest foot. That's going to be approximately 15 feet. Okay, so that's based on this model. If your diameter breast height is 12 inches, basically a foot across, we expect the height to be about 15 feet. Then D is estimate the DBH of a black walnut that's 25 feet tall. Okay, so here, that's the other way. We've done this kind of thing before. For Y, our height, if the height is 25, we're going to find X. Okay, so from our model, we're going to have is Y is equal to 25 is equal to 1.66 times X, which is our unknown, minus 5.14. Make sure there's like a 4 there. Then just solve for X. So 25 minus 5.14, subtract that, is 19.86. And that's equal to 1.66x. And then if we just divide that, x is going to be equal to approximately, I'll do two decimal places, 11.96. And what that means then, rounded, round the nearest inch. And so that's going to be x is approximately 12 inches. So once again, based on this model, if your tree height is 25 feet, put the feet in there, then we expect the diameter at this chest height to be a foot, or basically 12 inches. Okay, so let's kind of review what we did. So we looked at is basically understand the basics of what a regression model is, just a mathematical model used to predict data values. Okay, in this case, we'll look at a linear regression line. So if we have X and Y coordinates are in two dimensions, we have two kinds of data. We try to fit those together, get the line that best fits those, best fits all the data, even though it itself may not be great. You saw in this example here, although that was the best fit, still you see a lot of data points don't fit well on that line. We talked about how the slope is related, what the slope means, how it relates, how we can interpret it. So how to create scatter plots, and that's usually what you base your best fit lines off of. Then we explain what interpolation and extrapolation. All right, have a good day.